A Joule thief is a minimalist Armstrong self-oscillating voltage booster that is small, low-cost, and easy to build, typically used for driving light loads. It can use nearly all of the energy in a single-cell electric battery, even far below the voltage where other circuits consider the battery fully discharged. Hence the name, which suggests the notion that the circuit is stealing energy or joules from the source. The term is a pun on the expression Joule thief, one who steals jewelry or gemstones. The circuit is a variant of the blocking oscillator that forms an unregulated voltage boost converter. The output voltage is increased at the expense of higher current draw on the input, but the integrated current of the output is lowered and brightness of a luminescence decreased. History: in the Ingenuity Unlimited section of the November 1999 issue of Everyday Practical Electronics, page 804, Z. Kaparnik from Swindon published a simple circuit entitled Microtorch Circuit. The circuit consisted of a transformer feedback single-transistor voltage converter based on the blocking oscillator, which originally used a vacuum tube/thermionic valve and dates prior to World War II. The name Joule thief was coined by Clive Mitchell and given to his variant of Kaparnik's circuit, which consisted of a single cell, a single BC549NPN transistor, a coil with two windings, a single resistor, and a single white LED. Description of operation: the circuit works by rapidly switching the transistor. Initially, current begins to flow through the resistor, secondary winding and base emitter junction, which causes the transistor to begin conducting collector current through the primary winding. Since the two windings are connected in opposing directions, this induces a voltage in the secondary winding which is positive, which turns the transistor on with higher bias. This self-stroking positive feedback process almost instantly turns the transistor on as hard as possible, making the collector-emitter path look like essentially a closed switch. With the primary winding effectively across the battery, the current increases at a rate proportional to the supply voltage divided by the inductance. Transistor switch-off takes place by different mechanisms dependent upon supply voltage. The predominant mode of operation relies on the non-linearity of the inductor. As the current ramps up, it reaches a point, dependent upon the material and geometry of the core, where the ferrite saturates. The resulting magnetic field stops increasing and the current in the secondary winding is lost, depriving the transistor of base drive, and the transistor starts to turn off. The magnetic field starts to collapse, driving current in the coil into the light-emitting diode, and the reducing magnetic field induces a reverse current in the secondary, turning the transistor hard off. At lower supply voltages, a different mode of operation takes over. The gain of a transistor is not linear with VCE. At low supply voltages, the transistor requires a larger base current to maintain saturation as the collector current increases. Hence, when it reaches a critical collector current, the base drive available becomes insufficient and the transistor starts to pinch off, and the previously described positive feedback action occurs, turning it hard off. To summarize, once the current in the coil stops increasing for any reason, the transistor goes into the cutoff region. The magnetic field collapses, inducing however much voltage is necessary to make the load conduct, or for the secondary winding current to find some other path. When the field is back to zero, the whole sequence repeats. With the battery ramping up the primary winding current until the transistor switches on. If the load on the circuit is very small, the rate of rise in ultimate voltage at the collector is limited only by stray capacitances, and may rise to more than 100 times the supply voltage. For this reason, it is imperative that a load is always connected so that the transistor is not damaged. Because VCE is mirrored back to the secondary, failure of the transistor due to a small load will occur through the reverse VBE limit for the transistor being exceeded. The transistor dissipates very little energy, even at high oscillating frequencies, because it spends most of its time in the fully on or fully off state, so either voltage over or current through the transistor is zero, thus minimizing the switching losses. The switching frequency in the example circuit opposite is about 50 kHz. The light-emitting diode will blink at this rate, but the persistence of the human eye means that this will not be noticed. When a more constant output voltage is desired, the Joule thief can be given a closed-loop control. In the example circuit, the Schottky diode D1 blocks the charge built up on capacitor C1 from flowing back to the switching transistor Q1 when it is turned on. Zener diode D2 and transistor Q2 forms the feedback control, when the voltage across the capacitor C1 is higher than the threshold voltage formed by Zener voltage of D1 plus the base emitter turn-on voltage of transistor Q2. Transistor Q2 is turned on, diverting the base current of the switching transistor Q1, impeding the oscillation and prevents the voltage across capacitor C1 from raising even further. When the voltage across C1 drops below the threshold voltage, Q2 turns off, allowing the oscillation to happen again. If the load requires even lower ripple, in this example some delicate digital circuitry like a microcontroller, a linear regulator can be used after this to smooth the ripple out. Competing systems. U.S. Patent 4,734,658 describes a low-voltage-driven oscillator circuit, capable of operating from as little as 0.1 volts. This is a far lower voltage than that at which the Joule thief will operate. This is achieved by using a JFET, which does not require the forward biasing of a PN junction for its operation, because it is used in the depletion mode. In other words, the drain source already conducts, even when no bias voltage is applied. The 658 patent is intended for use with thermoelectric power sources, which are inherently low-voltage devices. See also, flyback converter. References. External links. French, video make Joule thief, Joule thief simulation. Supercharged Joule thief has high efficiency, simulation and efficiency comparison of different Joule thief versions, US 4734658, Google Patents listing for JFET version of Joule thief, espacenet.com, CA1303154, low voltage driven oscillator circuit, priority date August 14, 1987, Joule thief, modified version, 1, Clive Mitchell on making his original Joule thief.